In this video, I want to give you an intuition for coming up with those kind of soft assignments in a way that's a little bit more rigorous than what we had done before. So here's the setting. So if you have just one lambda, then what you're saying is, well, all the k's are generated by this lambda, so by Poisson of this lambda, right? So what we want to do is we want to maximize this likelihood. How do you do it? Well, you set the derivative to 0, and what you get is this equals 0, and you solve, you say lambda is the average of the k's. Great. So now let's go back to having two lambdas. We don't know which lambda generated which k. So what to do? Well, one thing we could do is we can say, okay, we wish we knew the z, so we'll just condition on, right? So what we want to do is if we knew the z's, we would want to maximize this. Because if you know the z's, everything's easy, right? If z equals 1, then you assign the k to pile number 1. If z is equal to 2, you assign the k to pile number 2. And you do maximum likelihood on the two piles separately. You get your lambda 1 and lambda 2, you're done. Can't do that, so because we don't know the z. So what we'll say is we'll do the next best thing, right? So we'll compute the expectation of this guy. So we'll treat z as a kind of random variable, and we'll compute the expectation of the likelihood. And then what we'll do is we'll maximize this expectation with respect to lambda and pi, and hope that that'll give us something good. So, okay, what does it mean? So for a single training case, if I take this expectation, it means I'm just taking the weighted sum of this guy, and I'm weighting it by the probability that z is equal to 1 and z is equal to 2. And here, how do I know the z at all? Well, I'm assuming that I know the lambda and the pi, and of course I know the k, so I can compute some kind of thing. So what is it going to be? So it's going to be, I'm just using the definition of the expectation, it's going to be the sum over the possible values of z, right? So z is going to be in 1, 2. The probability that zi is equal to z, where z goes over 1 and 2, right? Given, k, and we don't really care about all the k's, just ki and lambda and pi, times the log probability of ki given zi is equal to z, and lambda and pi, like that. Okay, so here I'm just using the definition of the expectation. So the nice thing here is that if I know the lambda and pi, this is easy to compute. In fact, we did it before. This is the wi1, wi2. Okay, so we can rewrite this as the sum, where z is in 1 and 2, of wiz, so this wi1 or wi2, of the log of pki given zi equals to z, lambda, and pi. Okay, so this is not a number, this is a formula. What we're saying is that if we want to compute the expected log likelihood, if we treat z as a random variable, then this is what it's going to be. Okay? So at this point, this thing we know how to compute, right? So this you can compute using the PMF here. So this is just going to be the sum, where z is in 1, 2, of wiz times log, let's write it out. So here, the k is ki, and then the lambda you choose, either lambda 1 or lambda 2, depending on the value of z, right? So that's going to be log of e to the minus lambda z times lambda z to the ki divide ki factorial. Okay, and this log we can just compute, so we can just do it now. So that's going to be equal to the sum over the z's, where it's in 0, 1, wiz, And now what's this? So this is e to the minus lambda z. Take the log of that. That's just going to be minus lambda z. And then this is going to be plus ki log lambda z. And this is going to be minus ki factorial. So this is nice because this should remind you of what we got when we were computing this. So let's go a little bit further. So now that we have this, let's say that we want to take the derivative of this guy with respect to lambda 1. Why not, right? So what is it going to be? So what we want to say is d by d lambda 1 of this expectation, so of Ez given k lambda pi log pki given zi and lambda and pi. What is it going to be? So it's the expectation of this guy. So this is the derivative of this guy. Well, this is going to be just here, you know, you don't really care about the terms that involve lambda 2, you just care about the terms that involve lambda 1, so you don't need the sum. You can just write wi1, and here you would write, this is a minus 1, because, you know, you do d lambda 1, d by d lambda 1 of minus lambda 1, that's just minus 1. And this is going to be ki divided by lambda 1. All right? So this is the derivative of this term. So at this point, we can kind of forget all this because this is the important thing. We're almost there. What we're trying to do is we're trying to maximize this thing with respect to lambda and pi. So we know the derivative of this guy. So let's just write the derivative of this guy. So the derivative of by d lambda 1, and you do lambda 2 the same way, of e, and this is with respect to z, k lambda pi of p, and here I'll just write k and mean k1 through kn, given the z, the lambda, and the pi. What is it going to be? Well, you are just taking the derivative of essentially the sum of p of k1 and p of log p of k1, log p of k2, log p of k3, and so on, right? So the derivative of the sum is going to be the sum of the derivatives. So it's just going to be the sum of those guys. So it's going to be, and you can kind of derive it carefully as well, the sum over I of wi1 minus 1 plus ki divided by lambda 1. So isn't that nice? Because this expression is very much like this expression. Okay? And in fact, if you set it to 0, what you'll get, and it's a very easy computation, is that lambda 1 is equal to the sum of wi1 ki divided by the sum of wi1. It's a very easy computation to do. From here to here, it's easy. And this is exactly the thing that we had before. So what's the key here? Well, the key here is that when we take the derivative, what we get is the weighted sum of the derivatives that we would have gotten here, where the weights are those probabilities of zi given ki and lambda and pi. Okay? This is not going to happen for us for every distribution, but it is going to happen for Poisson and Gaussians and things like that, where we can actually treat those weights as kind of like partial counts for cases. Because what we're doing here, we're saying take the derivative of this with respect to lambda 1 and with respect to lambda 2, and weight the terms using wi1 when you are computing the derivative. Okay, so what we were doing before is we would say, okay, so this is like an estimate for the total number of data points that were generated by Poisson lambda 1, right? And this is related to the fact that we are just weighting the ki here, the term that's related to ki rather, by wi1. This is going to be the case for some distributions. So again, what's the big picture? The big picture is we are saying, okay, if we knew the z's, things would be easy. We don't know the z's, so we'll just condition on them and treat them as if they're a random variable and pretend that we can compute the probability of the z's by fixing the pi and the lambda. And once we've done that, we can just maximize this kind of expression with respect to lambda and pi. In the EM algorithm, we would alternate between computing this formula and then maximizing in the M step with respect to the parameters. So in this case, the parameters are the lambda and the pi.